to measure porosity in conventional reservoirs, we use the helium-Boyle's law porosimeter. And it is so called because it uses helium as the gas that actually goes into the pore spaces, and then it uses Boyle's law from high school chemistry, as you will see. So here is a sketch of how the equipment works. There is a reference volume, V1, and typically it will be set to a pressure that is higher than the pressure in the sample cell, so that the gas can flow from reference cell into the sample cell when this valve is opened. It's important to realize that in the sample cell, the fluid can be stored in this empty space, right? And also in the pore space within the sample, but not in the grains within the sample. So the total space available for the helium to go into in this sample cell is not V2, right? It's V2 minus the sand grain volume. It's not V2 minus the bulk volume of the sample cell, because if you do that, then you don't account for the fact that the gas can be stored in the pore spaces within the sample. So the volume available for the helium to be stored in is going to be V2 minus Vs. And now we can figure out the total number of moles of helium in the reference cell plus the sample cell using the ideal gas law. You know, the real gas law is PV equals Zn RT, right? But at the low pressures we typically perform these experiments, Z is practically 1. So that's why we can use the real gas law, and we are looking for the number of moles N, and so N will be PV over RT. So to get the number of moles in cell 1, the reference cell, it's going to be P1 V1 over RT. RT is constant, right? And here is going to be P2, but not V2, V2 minus Vs, right? The space available for the gas to be stored in divided by RT, so that the total number of moles at initial conditions is the sum of these two. Then what we do next is to open up this valve and then connect V1 to V2, and then wait until the system reaches equilibrium. So why do we need to wait for the system to reach equilibrium? All of the assumptions we're making here is at equilibrium conditions. So we assume that the pressure in this sample space is going to be the same as the pressure in the pore space within the sample. And you will later see that this is difficult to achieve in shales because the pore spaces are so small and tight, and it takes a considerable duration of time before the pressure in the pore space will be equal to the pressure in the cell. But here we open it up, and then the gas flows from cell 1 into cell 2, and then we wait until the pressure in cell 1 is same as pressure in cell 2, and we call that the final pressure. And because these two systems are now connected together, we can calculate the total number of moles in the combined system as using the same ideal gas equation, and then it's going to be PF multiplied by the total volume available, which is V1 plus V2 minus Vs. And that's V1 plus V2 minus Vs together, right? And then RT is constant. So you notice this system was isolated from the environment throughout the duration of the experiment. What that means is that this number of moles at initial conditions, the total number of moles in this initial state, will be equal to the total number of moles at equilibrium. So we can write this on the left hand side and put this on the right hand side and equate them together. And that's how we calculate the solid grain volume. So that's the assumption. Mass is conserved. Number of moles at equilibrium is equal to number of moles at initial conditions. And then we've equated them together as shown here. And all we need to do is to make Vs the subject of the equation. So you see VS here and you see VS here. And then the question for you is, can you make VS the subject of equation? And then that gives you VS given all these other values which we know from the dimensions of the system and from the pressures at initial conditions which we can read from the pressure gauges. So if you get VS, the question for you is, can you describe how you will calculate porosity given VS and VB? You can pause this video here and see if you can come up with that. Come up with the expression for VS and come up with how you will calculate porosity given that VS and VB, because that's what you're going to need on the next slide. Here we are given an actual experiment, so hypothetical experiment I should say, because you will see here for simplicity we are assuming the sample is cubic, and then you're given these data on the experiment, and then the question is, can you find the porosity of the sample? So again, you can pause the video here and use the results you got from the previous slide and see if you can calculate this. But from the previous slide, what we had was P1V1 plus P2, the volume available for storage of fluid, right, was equal to the pressure at equilibrium multiplied by the volume V1 plus V2 minus Vs. That should be exactly what you have on the previous slide. It doesn't allow me to go back, but that's fine. So what happened to the RT? Because previously we divided each of these by RT. Well, you can multiply through by RT and that goes away. And so now you just need to expand this out. P1 V1 plus P2 V2 minus P2 Vs equals PF V1 plus PF V2 minus PF Vs. And you want to combine or group the terms in Vs together. Since we want to make Vs the subject of the formula, we can take Vs out, and this is minus V. So this is Vs multiplied by minus P2. On the right side is Vs multiplied by minus PF. So if you take it to the right side, this PF becomes positive. So we can write the PF first, right? So PF minus the P2 on this side. And let's take everything else to the right-hand side. So we have V1. Let's write V1 first. And then it's PF. There's V1 here. Take this P1, V1 to the other side. So it becomes minus P1, right? Plus, let's work on V2. So take V2 out. And then this is PF. And you take this P2, V2 to the other side. It becomes negative. And that's minus P2. Are we done? Not yet. Now divide through by PF minus P2. And then this goes away because you're dividing both sides by that. So that's your expression for Vs. Vs equals this equation. Now you have Vs. How do you get porosity? Porosity is pore volume divided by bulk volume, right? You are given bulk volume. It's the volume of the grain. So, but you're not given pore volume. So how do you get pore volume? VB minus Vs. So you're given VB, and then you use this equation to get Vs, and that's how you calculate porosity. So in this case, what are you given? Let's just write out what we're given. We're given, from the dimensions of the core, you're implicitly given bulk volume, right? The core is placed in chamber 1. Previously, in the previous slide, we placed the core in chamber 2. So all of these expressions have to be reversed such that V1 is now referring to the sample cell and not the reference cell. So everywhere they refer to chamber 1, we will change it to chamber 2 so that we can use these equations directly. That's the easiest way to set it up. So the core is placed in chamber 1, which has a volume of 120. So basically chamber 2, right? V2 is for chamber 1. It's basically what I've explained. Is 120 cc. It's hard to write here. VB is 100 cc, right? Cubic centimeter, 2 times 5 times 10. We don't need to worry about that. What else? Initial pressure. You're given initial pressure of chamber 1, which is cell 2. Chamber 2, you're also given the volume, so that will be V1, and the pressure for, and that's P1. I'm no more writing the values just for time. After the valve is opened, the pressure comes to equilibrium and the gauge reads this. So PF is precisely this. And now you can get VS. How do I know that? Do we have V1? Yes, right here. Do we have PF? Yes, right here. Do we have P1? Yes, right here. V2? Yes, 120 cc. That's this. PF, of course, we already had that. That's the 26.9. P2, we do. That's 0, right? And we already said we have PF and P2. So we have all these parameters. So plug in all these parameters given in the problem description, and you get your solid grain volume. And then from the solid grain volume, you get the pore volume as VB minus VS, 100 minus the VS you calculated, and you divide by 100, which is the bulk volume. And that's how you get the porosity.